Hello and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 1110, delete nodes and return forest. Before we read the question prompt, you guys know the drill. Please subscribe to the channel. It really helps me grow. Alright, given the root of a binary tree, each node in the tree has a distinct value. After deleting all nodes with a value in toDelete, we are left with a forest, a disjoint union of trees. Return the roots of the trees in the remaining forest. You may return the result in any order. So, as we can see, we're given this tree here, 1, 2, 3, 4, 5, 6, 7, and we're asked to delete the nodes 3 and 5. So, obviously, we're going to delete this node here and this node here. So, we want to return the roots of the trees remaining, right? Since we delete this 3, this 6 and this 7 become their own root, and deleting this 5 doesn't actually change the structure. So the new roots that we have are going to be, let's maybe use boxes here. So 6, 7, and 1. So that would be our answer here. We would want to return those as our answers because those are the roots of our new trees that are created. So it seems pretty straightforward how to solve this question. The issue is implementing code is actually a little bit more tricky. So let's think about how we can solve this in an intuitive manner. Okay, so we read the question prompt and we looked at a basic example, but it wasn't exactly clear how we want to solve this problem. So let's break it down and see if we can figure out how to solve this intuitively. So when it comes to our tree here, there's two types of node. One, which is going to be, we need to delete it, right? So to delete node. And then we have the second type of node, which is leave it alone, right? We don't want to do anything to it. Leave node alone, right? So obviously the trick here is going to be how we want to deal with the nodes that we want to delete. Because if we are traversing our tree and we get to a node that we want to delete, then we delete it, but we also have to deal with its children, right? So obviously, this is going to be a recursive one where we try to delete, smaller and smaller trees and then build our final answer. So, when we have to delete a node, that means that its children will automatically become, new roots, right? Once we delete this 3 here, this 6 and this 7 are now going to be roots of their own tree. But they could also be, staged for deletion, so we can't just add them to our answer just yet. We actually have to verify that they're not actually in that list. So what we want to do is we want to use a recursive approach. And what we want to do is, every time we go into our function, we're going to check, is our current node val, is it in, toDelete, right? Is it in the list of items that we need to delete? And if it is, then what we want to do is we want to delete it, and we just want to go into the DFS for its right child and its left child, right? So we want to say DFS on the left, and we want to go DFS onto the right. Okay, simple enough. But what happens if we don't want to delete a node, right? So in the other case where we don't want to delete a node, then what we need to check is actually, do we want to delete one of the children? So for this 2, obviously 2 is not in our toDelete here, but this 5 is. So if the 5 is going to get deleted, well, then we don't really want to kick off the depth first search from the 5 because we know that it has to go. We basically want to keep going from its children, but we have to basically take into account that this one is going to get deleted. So if it's going to get deleted, then we need to, basically we can ignore, we need to basically process the children of 5, but we also need to remove it from our 2 here. So we would need to set its, right child to be none, while also at the same time kicking our DFS from the 5 to basically see if its children can form any more, nodes. And we do the same thing for, the left and the right subtree. So, what we're going to do is if the current node that we're processing, we established that it's not, to be deleted. Now we're going to check, has left child. So if it has a left child and that left child is also, in to delete, then what we want to do is actually set that value to null. To delete, then we want to, set to null. And after we set it to null, then we want to kick off the DFS of that, left child to basically figure out if we can form any other, trees, right? And we're going to do the same thing for the right side. We're going to check, does it have a right child? And is that right child's value in the to delete set? If it is, then we want to basically set that node to 0 or to null in the parent, right? We want to set whatever, I guess this time we're talking about the right child. So we want to set the right child to be null. And then we want to DFS into the right child to basically figure out if we can form any more trees here. So that's the general gist. It's a little bit confusing when you look at it on paper. I'll admit it's not the best site to kind of walk through it with, me squabbling with my mouse or scribbling with my mouse. But let's actually go to the code editor now, and I will walk you through it line by line, and it's going to become a lot clearer. So, sometimes drawing it out is really helpful. Other times it's kind of hard to do, especially with a mouse. So let's, stop chatting. Let's go to the code editor and type this out because it's a lot clearer once you see the actual code. Okay. We're in the code editor, and I've promised you that it's going to be much clearer, so let's type this out. The first thing that we want to do is actually transform our to delete set to an actual set, right? Because it's given to us as a list, but in order to do quick lookups, we want to use a set here. So we need to transform this into a set. So we're going to say to delete is going to be a set. We're going to just transform it to a set. That way we can have big O of 1 lookups in that set. Okay, now we need a variable to store our solution. And remember, the solution is going to be all of the nodes, which are now the new trees, right? Once we've chopped any sort of like parents that were in the to delete set. So we're going to say self.forest, which is going to represent our answer, is just going to be an empty list. Now what we want to do is we're going to call a DFS function on our root. We're going to pass in the items we want to delete, and we're going to pass in a variable which marks whether or not the current node that we're processing is a root of a tree. And we'll explain this in a second, but it's necessary for us to know whether or not the node that we're working with is an actual root, because we have to do a few things if it is. So basically true if the current node is a root of a tree, and false if it's not. So once we call the DFS, we will have basically solved our question, and all we need to do is just return self.forest. So now for the tricky part of actually implementing the DFS function. So we're going to say def DFS, we're going to pass in self, the current node we're processing, the to delete set, and then whether or not the current node is a root. So the first thing that we want to do is, obviously, if we get to a node that's null, there's nothing for us to do here, so we simply just want to return and exit out of our DFS. So we're going to say if not node, we're just going to return, right? Nothing for us to do. Now what we want to do is, if our current node is actually needing to be deleted, then what we want to do is we just want to continue processing its left and its right child. Remember that when we see a node who has a child value that needs to be deleted, that's actually when we set that relationship to be none. So there's nothing for us to do when the current node has a value that's in to delete. We just continue through its children. So we're going to say if node.val in to delete, what we want to do here is we just want to call our DFS function on node.left, and we want to pass in to delete, and we want to pass in true for the fact that its child will now be its own root. Remember, if you look back to our diagram, if we look back to our diagram here, after we delete this 3 here, then the 6 and the 7 become roots of the new trees. So that's why we would pass that those children are going to be roots when the actual parent is in the to delete, right? Makes sense. So we do the same thing for the left and the right. So self.dfs node.write to delete, and we're going to pass in true. And that is basically what we do when the current node needs to be deleted, and it will have already been deleted at this point. So otherwise, what we want to do is we want to check the left and the right children of our current node. So let's check whether or not it actually has a left child. So we're going to say if node.left, and we want to check whether or not that node.left now is actually in our to delete, because we need to actually reflect that in our current node. So we're going to say if node.left.val in to delete, then what we want to do is we want to call our DFS function on that left child, because we still need to process it. So we're going to say self.dfs node.left. We're going to pass in to delete, and now that left child is going to become a root. And what we want to do is we want to say node.left is going to be equal to none, because we're deleting it from the current node. And otherwise, if we're not deleting it, then we just want to continue it with our DFS. So we're going to say self.dfs on the node.left, passing in the to delete, and this time we're actually going to be passing in false, because that new node will now not be a root. So we want to pass in a false here and continue. Now we want to do the same thing for the right child. So we're going to say if node.write, we're going to say if node.write.val is in to delete. What we want to do is we want to say self.dfs node.write to delete, and we want to pass in true again. So basically the same thing, and remember that we need to set that right value to be none, so we're going to do that. Otherwise, if it's not in that to delete, so basically if this if statement doesn't fire, what we want to do here is we want to say self.dfs on the node.write to delete, and we want to return false for the fact that that node is not a root, because it's still connected to the parent. So at this point, what we want to do is the last thing we need to do is actually check whether or not our current node is a root, because if it is a root, then what we need to do is add it to our list of forest nodes. So we're going to say if is root, then we want to add it to our forest, because if it's a root, then obviously we want to add it to the forest, because the forest represents all of the individual root nodes in our I guess forest here. So self.forest.append the node. So that's really all we need to do, and it would basically give us our solution. So let me run this, make sure I didn't make any stupid syntax mistakes. Sometimes I misspell things. Looks like it's fine. Submit this, and we are good to go. So solution accepted. All right, what is the time and space complexity for this algorithm? Well, for our solution, all we're going to do is do a depth first search through our through our tree. And doing any sort of depth first search through a binary tree is just going to be a big O of n runtime, where n is the number of nodes in the tree. And then also we need to take into account the fact that we do the to delete set here. So this is going to be big O of d, where d is the number of distinct elements in to delete. It could be the case that actually to delete contains all of the nodes in the tree. So it could be the case that this is the same runtime complexity as big O of n. So this is going to be big O of n, which is the cost it's going to take for the actual traversal, and the space time complexity for the actual to delete set conversion is going to be big O of d. So for the space complexity, similarly, we have to store big O of d elements in this to delete set, and then for the actual DFS, it's going to be big O of n in terms of the actual stack frames for the recursion here. So our runtime complexity is basically the same as our spacetime complexity, big O of d plus big O of n, where remember n is the number of nodes in the tree and d is the number of distinct elements in to delete. So that is how you solve delete nodes and return forest. It's a bit weird. It took me a while to figure out how to do this, particularly figuring out that you need to keep track of which of the nodes are actually root nodes. And once that kind of clicked for me, the solution fell into place. But otherwise, it is basically just a depth first search through a binary tree. So nothing too complex in terms of execution, just a few weird things you need to notice. Otherwise, not that bad. So that is how you solve this question. If you enjoyed this video, please leave a like and a comment. It really helps me with the YouTube algorithm. If you want to see more content like this, please subscribe to the channel. I have a lot of videos already created and I plan on making a whole lot more. So subscribe and hit the notification bell so you don't miss those. Otherwise, thank you so much for watching and have a great rest of your day.